Now we've recently had a look at differentiation by first principles. Now we're going to differentiate or find the derivative of a polynomial function with a rule that you'll be glad to know speeds things up quite a bit. Okay, now that's not to play down the importance of the first principles, but the rule does help us, day by day, as it were. And so we're looking at a polynomial situation. However, let's go term by term. Each term in a polynomial is of this form here, x to the power n. So x being an independent variable and n is a positive integer. But you can even see sometimes that n is 0. More about that later. So far, if you've been watching the previous videos and been working on this, have you noticed so far that if we take the derivative of something like x to the power 1, which is just x, the derivative is a constant 1. The derivative of x squared, which you've definitely seen in the previous videos, comes out as 2x. The derivative of x cubed type terms comes out as 3x squared. There is definitely a pattern here, and in general this is the pattern, and you should take note of the following. It can be proven, although we're not doing a proof in this video, it can be proven that for any function x to the power n, where n is a natural number, a positive integer, the derivative is n times x to the n minus 1. Very important. So n is a positive integer or a counting number. But even having said that, we can deal with when n equals 0. Let's deal with that now. In fact, if we look at some examples, let's deal with the weirdest one first. So what's the derivative if f of x equals a constant? Let's say 5. Now 5, using our index laws, not that you would do this, but 5 can be written as 5x to the power 0. Now x to the power 0 equals 1, because anything to the power 0 is equal to 1. So what would happen if we applied this rule? So yes, I'm doing the weirdest one first. F dash of x, so what you do is get n. Now n here is 0. So it equals 0. Now we've got x. In fact, we've got 5 as well. I'll show you the rule for this later. You have to multiply the 5 on as well. We have 5x to the n minus 1, 0 minus 1. Perhaps I shouldn't have showed you this one first, but don't worry, it will make sense. So 0 times 5 times x to the 0 minus 1. Well, 0 times 5 is 0. X to the 0 minus 1 is x to the negative 1. Now, we look at that more, but really 0 times anything is 0. So when you take the derivative of a constant, it comes out as 0. So that's actually a result. So that the derivative of a constant is 0. So that's a result. Let's look at a less weird one. How about if we have f of x equals x to the 7? Alright, so perhaps this is the one I should have started with, but look, we've got to take funny little risks sometimes, don't we? So using our rule and the pattern that always exists for these sort of terms, n times x to the n minus 1. So n is 7. So we have 7x to the 7 minus 1, which would be 7 times x to the power 6. And that's the result. And if you did that by first principles, you would get that same result by taking the limit. Now, before we go further and apply this to polynomials with several terms, we need to recall a definition of a polynomial. which is from our earlier studies. A polynomial of degree n is a function in this form here. So it's got various coefficients, and it can be varying lengths, suggested by those ellipse points there, and it may end in a constant. Any of these terms here may be absent too. They don't all have to be there. The other thing to note is the x to the n form. So that means that they go down in order. Again, you don't have to have all of these. They can be missing. So you've heard of things like quadratics, cubics, linear functions, quartics. They have integer, or in fact, to be more accurate, natural number indices. Okay, so these little things that it's raised to are natural numbers for it to be properly classified as a polynomial. And lastly, the plus doesn't have to be a plus. If you plus a negative value for the coefficient, so if one of these yellow terms was negative, it actually would be written down as subtraction. So that's what defines it basically. So if we have something like, let's say, you might be sick of me using f of x, let me use g of x now. So let's say we had, going back to that one, we had that funny 5 and that was a bit awkward. Let's do something slightly different. Let's use the 5, but let's say it's 5x to the 9 now. The derivative of 5x to the 9, how do we deal with that now? It's not just x to the 9, it's 5x to the 9. So basically what we do with that is, well, it's a couple of ways about it. Okay, you could say it's so it's 5 times the derivative of x to the power 9. Now that's not, I would not normally write things down that way, but we haven't done the notation properly yet. So basically that's how you do it. So basically the derivative of x to the 9 is 9x to the 8, and we just multiply 5 on the front, so we have 45x to the power 8. So that's not set out properly. Let's formalize it properly now. So looking at that, if f of x equals k, where k is a constant, so some real number, k is a constant. If f of x is a constant times some other function, the derivative is that same k times the derivative of that function there. Alright, and need to get a note of that, and that's what we did there, because there's the constant and there's the derivative of that function x to the power 9, and we put it together, multiplied together, and 5 by 9 made the 45. So that's an important one. So in other words, you can take the derivative of the function and just leave the constant separated as such and then multiply it through at the end. What if we have a sum? Alright, so we have a polynomial made of the sum of two terms. They're sort of ax to the n type terms. So we call that function b of x, just so we're given that. How do we find the derivative of it? Well, basically you find the derivative of each of these. So you find the derivative of the first one, which would be, that's the result we've got just above there, and that's 45 times x to the 8. And then we do the second one separately, so we've got 10 times, now it's n times x to the n minus 1, and then we just tidy that up, 45x to the power 8, which is added to 60x to the power 5. So in general, for sum, we do it this way. So basically, if we have a function that's made up of two other functions added together, which is an accurate way of describing that, you just find the derivative. To find the derivative overall, you find the derivative of each part and then you add it together, which is exactly what we did in that example. What about a difference? Well, it's the same. So if we have the following, if we have 2x cubed minus a half x squared, so you can don't have to have integer values for the coefficients, as you know. So that would be 2 times, now it's n times x to the n minus 1, so it's 3x to the 3 minus 1 is 2. Now minus a half, and we've got the x out the front. X minus 1 would be that, and so we'd have 6x squared minus x. Thus, if f of x equals g of x take h of x, f dash of x, the derivative, is g dash of x take h dash of x, which is essentially the same rule for sum and difference, barring the sign in the middle.